This is the lecture on refraction of light. If you look in this picture, you'll see light coming into water, hits the air-water interface here between the two materials. So it's traveling in air up here. When it starts traveling in water, it actually bends when the light wave slows down. And we'll draw a normal line right here at this point of refraction. And we'll see that this light wave bends towards the normal when the light wave slows down. In this lecture, we have speed c of light in a vacuum. So c is 3 times 10 to the 8th meters per second, and we use v as the speed of light in the material. C is the speed of light in the vacuum or in air, either one. Here's an example of light traveling from one medium to the next. What happens is you'll see that this light is bending towards the normal because that light wave is slowing down. And so we have this red light coming in, hits the interface, bends towards normal, bends inward, and because the light is slowing down. Over here you see the index refraction is 1.33, and if I increase that, you'll see it bend more. If I go to like 1.52, you'll see it bend a little bit more, and if I go to diamond, you'll see even bend more. Okay. Here you'll see incident angle, index refraction, incident wavelength, and this is in nanometers. Nano means 10 to the negative 9th. Refractive wavelength here in nanometers, and the refracted angle. And there's a relationship between all of these different variables. It's called Snell's law. First, we're going to look at the definition of index refraction. And the index refraction n of a material is the ratio of the speed c of light in a vacuum to the speed v of light in the material. So you'll see the equation right down here. N equals c over v. And that's exactly what index refraction is. You saw that water was 1.33. Well, the ratio between speed of light and the speed of light in a vacuum and the speed of light in the water has a value of 1.33. Some other examples of index of refraction, for diamond it's 2.419, crown glass 1.523, ice is 1.309, and water is 1.333. As a matter of fact, this is why you can see ice when it is in water. So let's now try a problem. Find the speed of light in lucite. So pause the video and see if you can use the previous equation to see if you can solve this problem. Hopefully you use the n equals c over v, plugged in your values. Speed of light in a vacuum, remember, is 3 times 10 to the 8th meters per second, so your final answer should have been 2 times 10 to the 8th meters per second. Now we're going to look at Snell's law. And in this case, if you look up here on top, you see this light ray coming in, going from air to water, and as we saw before, it's going to bend towards this normal line. This normal line is right at the point of refraction and actually reflection, because as you remember in the Slinky lab, you have partial transmission, partial reflection. So this light ray will bend. So theta 1 and theta 2 are not equal, but theta 1 and theta 1 are equal. And then also we'll have to look at, well, what happens when light comes in from water and goes out into air? And you'll see that instead of going in a straight line, it actually bends away from the normal because the light ray is speeding up. It also does, since you're going from one medium to the next, you also have partial reflection. And you'll see that this theta 1 here are equal. Okay, here we have light going from this one medium to the next medium. This is a sideways view of light traveling from one medium to the next. In the previous example, we had a vertical view. So just make sure you understand that what this view is going from one medium here, the white medium, into the yellow medium. And watch what happens when I change the index refraction of the first medium. We keep the medium 2 at 2.0. And look what happens when I'm right at 2. When they're both at 2.0, it goes straight through. And then look what happens when it gets larger than 2.0. Medium 1 is larger than 2.0. So when it goes from medium 1 to medium 2, it's now speeding up, bending away from the normal. And then if I go ahead and bring it back down like this, I change medium 1 to be less than 2.0, you'll see that it bends towards the normal. And I can also change medium 2 as well. I can do different things with it to make the angle be different. I've made medium 2 1.0. Now look what happens when I make the medium 1 have an index refraction that gets larger and larger. And you'll notice eventually its index refraction gets so large it's right about 90 degrees. And if I go beyond that 90 degrees point, it then has what's called total internal reflection. And we'll look at that more later. But at this point right here, I've gone beyond the critical angle, and no light cannot penetrate through that interface. Over here, our angle is less than the critical angle, and so light can pass through. The equation that explains this refraction is called Snell's law, law of refraction. N1 sine theta 1 equals N2 sine theta 2. The ones mean the subscript is the material 1, and the subscript 2 is material 2. And if you look at this picture up here, air is material 1. And so theta 1, you'll have your N1 here. And then the second material is N2, which has its index refraction 1.33, and theta 2 is down here inside the material. You always measure your angles from the light ray to the normal line. So here are some rules for us. We should write these down in our notes. As light goes into a more optically dense material, means it has a high N, high index refraction, it will slow down and bend towards the normal. As light goes into a less optically dense material, it has a lower N, it will speed up and bend away from the normal. So here's an example of that. How does the speed of light change as the light changes medium? So I would like you to pause the video and ask yourself, as the light goes from liquid A to liquid B, is the light ray speeding up or slowing down? And as it goes from B to C, does it speed up or slow down? So go ahead, pause the video and think about that. The answer is that when it goes from A to B, it speeds up because it bends away from the normal. And then when the light goes from B to C, it slows down because it's bending towards the normal. So here's a problem that we'll have. A light ray strikes an air-water surface at an angle of 46 degrees with respect to the normal. The refractive index for water is 1.33, and we know for air it's 1.0. Find the angle of refraction when the direction of the ray is from the air to water, and then when it's from the water to air. So pause the video, try this, and see if you can come up with the answers. You're going to use Snell's law to do this. And I would say draw the picture and see if you can figure out how to do this. Okay, here are your answers. For the first problem, you get 33 degrees, and then for part B, you get 74 degrees. You can pause the video and see how this has been done, but it's been done using Snell's law. You'll look up here, this equation up here is just Snell's law with the N2 cross-multiplied across. An example of what we've been talking about is the rear view mirror that you have in the car. During the day, your rear view mirror is a certain way so that if you look over here, your day setting in picture B, the light from the car behind comes in, it refracts in the glass, and you get this reflection here at position A. You'll get partial transmission, partial reflection. But the light continues through, it slows down, bends towards the normal, reflects off of this mirror back here at B, so you'll have angle of incidence equals angle of reflection. Then that's just a pure reflection right there. Coming out, you have light going from glass into air, and so you have partial reflection right here and partial transmission, and you'll see that the light bends away from the normal, bends up when it speeds up. And then you adjust your rear view mirror so that the light that you want to see goes into your eye. If you go down here, this is the night setting. You pull that tab, and what happens is, see how the angle of this mirror changes as you come over here? The light's now different. And so what happens is, the light that comes from the car behind, when you change that angle, that majority of that light goes up this way. This is the light you used to see. This is the same light that used to go in your eye up here at position D. But now what you look at is this reflected ray. So see this light over here at position A? That's what you now see going into your eye. So that's a lesser amount of light. You can still see the car behind you because it's dark out, but you're not blinded at this point.